Welcome everyone. Welcome to our Caltech Astronomy public lecture. This is our June lecture, and I'm Dr. Cameron Hummels. I will be the MC for this evening. Thanks everyone for coming. The schedule for tonight is that we will have, after a few minutes of announcements from me, I'll introduce our speaker, Ryan Rubenzahl, who will speak for about 30 minutes about exoplanets, planets orbiting around other stars. And then we'll immediately go into a Q&A panel consisting of 6 members of our department who either have PhDs in astrophysics or soon will in the next couple of years, who work on a variety of different subject matters. And we'll talk, we'll receive questions from all of you, either on questions related to the topic of Ryan's talk on exoplanets, or if you have other questions about astronomy and space science and physics that you'd like answered, you're free to type them in the comments section at the bottom of this YouTube page, and we'll address them. You can ask those questions right now. You can ask those questions throughout Ryan's talk. We'll write them down and try and respond to them over the remaining time that we have tonight until 9 o'clock Pacific time. So as I mentioned, this is a monthly event. I haven't yet scheduled the date for our July event, but I will soon. I'll post it here and on our social media and on our website on Caltech Astronomy. In addition to these monthly events, we have a slightly less formal, slightly more raucous venue for astronomy education called Astronomy on Tap. Those are events which we originally held at a bar in Old Town Pasadena, but obviously during the pandemic and the shutdown, we haven't been able to do that. So we've been offering them in a virtual form on YouTube Live as well. So up until recently, that was scheduled for this coming Monday. Our next one is, we've postponed it a week, so it will be on June 22nd. If you go down to the YouTube page, it will show, it'll show the scheduled event, so you can click like set a reminder or whatnot. It'll be at 7:30 a week from Monday, and it's going to be on gamma ray bursts and meteorites, space rocks. So it'll be super cool. And we'll also have astronomy themed pub trivia that will happen during that. So it's really fun. As you may have noticed, we were originally scheduled to have this event last Friday, but we postponed it due to the ongoing Black Lives Matter movement and all of the protests going on. We didn't want to provide a distraction against that because we think it's a really important moment for society and for our country to address some of the injustices that have been facing the Black community for centuries. As part of that, this Wednesday, much of academia shut down. Certainly in the astronomy departments at various universities, this was the case, and this was true at Caltech as well. Most people stopped doing their science for the entirety of the day on Wednesday and focused their attention instead on ways to correct these historical injustices that have been facing the Black community, not just on a societal level, but also specific to astronomy. For instance, in astronomy and physics, fewer than 2% of all PhD holding astronomers are of Black descent, which is a horrible misrepresentation based on population, and it's a horrible injustice. So a lot of the focus we had was on increasing public education efforts, changing the ways in which students are evaluated, or admissions committees operate, or hiring committees operate. And obviously it's just a start, but it is a start. So we hope this will be an ongoing effort that's taken up by the rest of the community of astronomy, as well as society as a whole. Okay, so in terms of our public lecture, normally we have a stargazing component when we do this in person. Obviously that isn't easily possible here doing over YouTube Live, but we can provide some analog of this. There's a sky visualization tool that is available called Stellarium that I'm just going to show you right here. Stellarium is a free open source code that anyone can download for free. It operates on Mac or PC or Linux, and it'll allow you to visualize what the sky looks like at any preferred time and any preferred location. This right now is showing us what the sky looks like tonight from Pasadena at at 10 o'clock p.m. I had to push it back because it's still light outside since we're so close to the summer solstice and the sun sets so late. So this is what the sky looks like at 10 o'clock tonight. And if you were to, well, from a really decent sky site where there's not a lot of light pollution, you can obviously see some things like this is the Big Dipper here. And because the Big Dipper, the pointer stars at the end of the Big Dipper will always point towards the North Star. So they point here, this is the North Star. So that gives us some framework. We're always looking north. So if you can find the Big Dipper, you can find north. But tonight, there's some various highlights that I wanted to point out. If you look in the eastern sky in the evening, you'll see what's called the summer triangle that consists of 3 really bright stars, Vega, Altair, and Deneb. And if you center on the middle of that triangle, there's a star called Albireo. And if you zoom in, which you can do with binoculars, or you can do, excuse me, with a telescope, you'll see 2 separate stars there. It's a binary. Now, binaries are reasonably common in the sky, 2 stars orbiting around each other. But in this case, those 2 stars are actually different colors. One is blue, the smaller one is blue, whereas the brighter one tends to be like an orangish yellow. Now, all stars have color, but we may not think of it that way because our eyes aren't very good at perceiving color in low light conditions. But if you use a telescope or something that enhances the brightness of these objects, you can make out the color, especially when there's 2 different colors right next to each other. So Albireo is a nice target in the sky. Furthermore, we're looking at Vega here. If you zoom in Vega, Vega is the 5th brightest star in the sky, and it will be the 2nd brightest visible tonight. You can see it's part of this constellation called Lyra, the harp, the lyre in the sky. And if you zoom in a bit at this end, there's a really special object called the Ring Nebula, which I can't quite seem to get. It's quite small, but it's a really incredible object. It's a planetary nebula, so this is what happens when a star like the sun reaches the end of its life. Rather than exploding, it kind of sloughs off its outer layers of gas, which continue to glow and fluoresce, much like this is. And yeah, like this is what will happen to the sun in several billion years. So it's kind of cool to see. It's very colorful. And then finally, the other cool thing to see, this is the constellation of Hercules. Of course, there won't be lines in the sky when you look up in the night sky, but you can oftentimes find it near Lyra with this nice little quadrilateral. And there's an object called the Great Cluster in Hercules that is it's a globular cluster of stars, a few 100,000 stars that are all orbiting around each other. And you can see this with your naked eye in dark enough skies like Death Valley or the Sierra, maybe even Joshua Tree, but it's better to have a telescope where you can start to resolve the individual stars. So really cool objects, but yeah, the summer sky is a nice time to observe. You just have to stay up a bit later in order to see stuff. All right, that's all I've got for stargazing tips. So I will invite Ryan to join us now, our speaker for this evening. Oh, there you are, Ryan. Okay, so Ryan Rubenzahl is a 2nd-year graduate student in astronomy at Caltech. He studies the demographics of exoplanets, especially small rocky planets like the Earth, and is building an instrument to measure the radial velocity of the sun to help push the limits of the radial velocity planet finding technique. So Ryan, I will leave it to you to take it away. Do you want to share your screen? There you go.
Okay, can you hear me?
Yeah. All right, I'll leave it to you. Thanks, Ryan.
Awesome, thanks Cameron for that great introduction. Hello everyone, my name is Ryan Rubenzahl. I'm a graduate student at Caltech, and tonight I'm excited to share with all of you how we actually measure exoplanets by measuring the speeds of their stars, and with the goal to find something like Earth 2.0. So I want to start tonight just with the basics, defining what an exoplanet is. So I'm sure we're all familiar with what a planet is, or at least planet Earth. The solar system has 8 planets, sorry to Pluto, shown here with the relative sizes to scale. But of course, the distances between these planets are very not to scale in this graphic. And the 8 planets together, along with the sun and all the other asteroids and comets and dwarf planets and dust, make up what we call the solar system. And an exoplanet is simply a planet that orbits some other star, not the sun. This is a shorthand way of saying extrasolar planet or outside the solar system planet. An exoplanet and its star together make up an extrasolar system. And this artist's conception here shows many stars in the night sky, which you can see are many of which are orbited by exoplanets, in some cases by multiple exoplanets, with all sorts of random orientations throughout space. So how do we actually detect exoplanets? How do we even know that these are real things in space? Well, there are a number of ways, most of which are indirect. There's one way where you can actually directly image the exoplanet, which is very difficult, and I'm not going to talk about that at all. There's one of the recent lectures in this Caltech Astronomy Outreach Series by Jason Wang on our YouTube channel. You can check out to see how to actually take pictures of planets. But the methods that I'm going to focus on are indirect. And by that, I mean we observe the influence that a planet has on its star by measuring the light from the star. And we don't actually see the planet directly, we infer its presence based on how it affects its star. So one way to do this is called the transit method. In this case, we're observing the overall brightness of the star over time. And if we happen to be viewing an extrasolar system edge on to the planet's orbit, then each time the planet orbits, it will pass between us and the star, blocking a little bit of the star's light, which we can measure as a dip in the measured brightness of the star. And this is called a transit. And a larger planet will cover more of the star and block more light than a smaller planet. And so this technique lets you measure the relative size of the planet compared to its star, as well as its orbital period, how long it takes the planet to go around in its orbit once. For the Earth, that's how we define what 1 year is. Then the orbital period is simply the amount of time between successive dips. And if there are multiple planets, like you can see in this animation here, sometimes you might have more than one planet transit at the same time, which can create some interesting shapes. You can see as these two pass overhead, what astronomers call a light curve, or just the amount of light from the star over time, showing both of the planets transiting. So another way to indirectly measure a planet, and this is the method that I'll be talking about throughout this lecture, is the Doppler method. And this was based on the Doppler effect, which I guarantee many, if not all of you, have experienced in the context of sound. So say we have an observer here, this green person, and this dot, which is emitting waves, which could be sound waves. If the noise is moving and say coming towards the observer, then the sound waves will start to get bunched up on that leading side, meaning the wavelength of those sound waves is smaller, which in the case of sound means that you would hear a higher pitch, right up until it passes you. And now as it's receding, you're hearing waves that are spread further apart, which for sound means a lower pitch. And this is what gives you that familiar sound of a car going past, where it sort of goes like, well, light also behaves like a wave, so it too obeys the Doppler effect. However, changing the wavelength of light corresponds to changing the color of the light, where for sound, it's the pitch, for light, it's the color. And in the visible part of light that we can see, blue is the shortest wavelength and red is the longest. So we would see something appear to be blue if it were moving towards us, and we very creatively name this blue shift. And likewise, it would appear red if it were moving away from us. You'd call this red shift. And my high school physics teacher taught me a great way of remembering this that has stuck with me till today. Just think of a baboon walking towards you. You'll see its blue face. And as it recedes away from you, well. Now, I know what some of you might be thinking mischievously in the audience. Green is bluer than red. So how fast would I have to go to make the red light in front of me look green? Well, if you do the math and calculate how fast you would have to go, the answer is about 100,000 miles an hour. So don't try this at home. So how do we actually use this to find planets? Well, as the planet is orbiting around its star, it's gravitationally tugging on the star and causing it to move in an opposite dance to the planet. although on a much smaller orbit because the planet's gravity is much weaker. Luckily for us, if we take the light from a star and separate out all its colors, for example, by using a prism, then elements and molecules in the atmosphere of a star will absorb light at very specific colors, which we see as dark bands where this light doesn't escape the star. And we can use these lines, which again, we creatively name absorption lines, as a reference. And if we see these lines moving back and forth from red to blue and blue to red, that means the star is periodically moving away and towards us once per every orbit of the planet around the star. And a bigger planet will have a stronger gravitational tug on its star, causing the star to move faster, which makes the amount that these lines shift back and forth greater. And again, with astronomy and creative names, we call this shift the Doppler shift. So while the transit method tells us the size of a planet, the Doppler method tells us its mass, how heavy it is, how gravitationally strong it is compared to its star. And so these two methods are complementary, and together they can tell us about the density of a planet and whether it is rocky like the Earth or perhaps gaseous like Neptune. So these two techniques have been prolific in finding exoplanets all over the galaxy. And this animation will show the discoveries over time, but before I start it, I want to explain basically what we're showing here. So we have the mass of the planet relative to Earth on the vertical axis, so just how heavy the planet is, and the orbital period in years along the horizontal axis, so how long it takes the planet to orbit its star. Note that the closer a planet is to its star, the faster its orbit will be, the faster it will move in its orbit, and so its orbital period will be shorter. So I might slip and say close in when I'm talking about short period. A planet closer to its star further will be hotter, while a planet more further away from its star will be colder. So the first exoplanet was discovered in 1995 called 51 Peg B. You can see it here in this mass and period diagram. And comparing it to solar system planets, you can see it's about as high up as Jupiter and Saturn. It's about the same mass, but it's much closer to its host star. It orbits much more quickly than even Mercury in our solar system, which means that it had a very strong gravitational tug on its star, and thus the Doppler shift it induced was relatively easy to see. This is why it was one of the first planets discovered. Then in 1996, I was born, and since then we have discovered over 4,000 exoplanets. The green points are discovered by the Doppler method and are typically more massive planets, while the red points are from the transit method, which really took off when the Kepler Space Telescope was launched in 2009. And this movie ends in 2017 with 3,000 planets. And since then, we have discovered upwards of 1,000 more. But already, even in just this diagram a few years ago, we can see many different classes of different exoplanet types. For instance, there's a group of massive planets like Jupiter that are very close to their stars, which we creatively name hot Jupiters. Likewise, there's a cluster of Jupiter-sized planets that are very far away, which we call cold Jupiters. You might also notice there's an apparent gap or lack of planets in this particular region. And you might think, well, maybe we just can't detect these yet. But any of these points down here, which are less massive, should have a weaker signal, and yet we detect them very frequently. So it's actually that planets don't exist here in nature. And we call this the hot Neptune desert. This is we think because if you take a planet like Neptune and put it very close to its host star, then the intense radiation from that star will blast away its atmosphere. And what you'll be left with is a rocky core, something more like an earthen mass. The kinds of planets that I'm most interested are in this oval right here. So not too hot, not too cold, kind of just right where you might think that liquid water could exist on the surface. We call this the Goldilocks zone. And where the mass is maybe a few Earth masses or less, so we expect it to be rocky. And this is where something like Earth 2.0 might exist. And so for the rest of this talk, I want to discuss just how difficult it is to measure these kinds of planets and why this oval remains unfilled. So to just represent the scale of how tiny the Earth is, let's make the sun an 8-pound bowling ball, which if we're talking regulation size is 8.5 inches across. Then proportionally, the Earth would be just a 2 millimeter grain of sand, just 10 milligrams in weight, sitting all the way at the 50-yard line. And what we're trying to measure is the gravitational tug on the bowling ball by the grain of sand that's at the 50-yard line, where we're making the measurement on the other side of the country. And as you can imagine, this is a very small motion. So here's an example of a star spectrum where we've taken the light from the star and split it up into all of its colors, from red at the top left to blue at the bottom right. And all of the dark bands scattered throughout are absorption lines caused by many different elements and molecules in the atmosphere of the star absorbing specific colors. And if we zoom in on the spectrum, we can watch the effect of the Doppler shift move these absorption lines back and forth across our camera pixels, which we will measure as having different amounts of light in each pixel as the dark band moves back and forth. And this Doppler shift illustrated here would correspond to a speed of around 500 meters per second in velocity, which is 1,000 miles an hour. If this were due to a planet, this would be something like a planet twice the mass of Jupiter flying around its star once per day. So even more extreme than 51 Peg-B. For Earth around the sun, our grain of sand around the bowling ball, this Doppler shift is just 9 centimeters per second, or 0.2 miles per hour. That's 5,000 times smaller than what is shown here, and 10,000 times smaller than a single camera pixel. That's so tiny that if we were to zoom in with an electron microscope, those absorption lines would be moving back and forth the width of just 5 silicon atoms inside that pixel. So to even have a hope of measuring this, we need to deal with a number of considerations. Taking a step back, what's happening overall is we have our observatory with a telescope. It's observing the light from the star, and it sends that light into a spectrograph, where we have something like a prism that splits the light up in all of its colors, and then we take a picture of that spectrum with the camera, and we see absorption lines from the star superimposed. Now, for very precise measurements, we need a really stable reference ruler. And by that, I mean something that we know the wavelength of extremely precisely, that we can sort of compare how much the star spectrum has been shifted. And one way this has been done historically is by placing an iodine cell that's been heated into the front of the setup. And that imprints the spectrum of iodine onto the star spectrum. And we know the spectrum of iodine very, very well from precise laboratory controlled measurements. And so what you then need to do is just look at how much the star's lines shift relative to the iodine. And if there are any errors due to different mirrors or lenses in the spectrograph, it should affect the star and the iodine equally. And so when you look at the relative shift, those errors should cancel out. And one big way in which that might happen is if the temperature inside the spectrograph changed. If it got warmer, materials would tend to expand. And if it got colder, materials would shrink. And if the distance between two mirrors were to grow or shrink by just 1 nanometer, that would make a fake Doppler shift on our camera of about 1 meter per second, which is like walking speed, which is significant when compared to the signals from Earth mass planets. So we definitely need to keep this whole thing very temperature stable. And when doing so, this iodine method overall works fantastically well and can reach precisions of about 1.5 meters per second, or 3 miles an hour. So we can get things a few times the mass of the Earth, but not much smaller. An alternative is to just make the spectrograph super duper stable. So shown here is an animation of the Keck Planet Finder, or KPF, as it will look when it's completed. This is in development currently and being led by my advisor, Andrew Howard. And KPF is using a novel technique where the instrument is being built on a special material called zero-dur. Zero-dur is the special mixture of glass and ceramic that effectively cancels out the effects of thermal expansion, which means that zero-dur has an extremely small response to temperature changes, 2,000 times better than stainless steel. For zero-dur, a change of just 1 degree Celsius will cause the lengths to change by just 0.7 micropercent. And on top of that, the whole thing is put in a vacuum chamber with 0.01 degree temperature stability. And so you can trust that the distances between all these mirrors and lenses that you can see the light bouncing around between is extremely close to constant. And KPF will rely on this intrinsic stability to reach precisions of just 30 centimeters per second, or 0.6 miles per hour, pushing us much closer to this goal of finding Earth mass planets. For comparison, the speedometer in your car is accurate to about 5% error. There are manufacturing laws about this. So if you're going about 60 miles an hour, your reading should be good to about 3 miles an hour. And comparing that to KPF, that's 5 times worse than KPF can measure the relative speed of another star. Of course, speedometers are also purposefully calibrated high so that this error will never give you a reading slower than you're actually going. So you can't blame the speedometer error for why you were speeding. And if you consider the relative precision to how fast that star is actually flying through space, which is something like 200,000 miles an hour, this is equivalent precision to measuring the distance from New York to LA to within 50 feet. Now, despite having instruments that are super stable, everything in the universe is moving, and we need to account for it if we wish to see the tiny change in speed of a star due to a small planet. So first, we need to realize that we're trying to make this measurement while on a moving platform. The Earth is spinning at about 400 meters per second, or 1,000 miles an hour. It's also revolving around the sun at about 30 kilometers a second, or 60,000 miles an hour. And the Earth, the sun, and the whole solar system are collectively moving through the Milky Way galaxy at speeds of about 220 kilometers per second, or something like 500,000 miles an hour. Luckily for us, we have a very long history of observations of the Earth and many satellites in space constantly monitoring the solar system. And so these velocities can be calculated extremely precisely using what we think is a really good understanding of gravity, thanks to Newton and Einstein. And using the exact moment that we observe a star, we can correct for all of these speeds to within a couple centimeters per second, which is remarkably good, in my opinion. You might also think, well, wait, the star is also moving through the galaxy at some random speed in some random direction. But what we really only care about is the relative change in speed due to the orbiting planet. And so as long as we can measure relative speeds precisely, we don't really care about actually how fast it is going. But we do still need to know the coordinates of the star on the sky and how fast the star is moving across the sky so that we're sure that we're looking straight at it. We're also looking through a very dirty lens called the atmosphere, which is bubbly and turbulent and moving all over the place, and not only blurs out the image of a star, but will also absorb some of the star's light, adding additional absorption lines corresponding to molecules in the Earth's atmosphere. And these can contaminate our data and cause additional errors. And so this is something that we need to study and understand and be able to correct for. On top of that, the atmosphere likes to make these things called clouds, which block our view of the sky altogether every once in a while, and that's never appreciated. And if we could get rid of clouds, I think we would. However, even with super precise instruments, and even on a perfectly clear, quiet night, the fundamental limit to being able to detect Earth 2.0 might actually be the stars themselves. So this is a movie of the sun, very zoomed in at extremely high resolution. And you can see just how bubbly the surface of a star is. There's these blobs of gas and plasma that rise up to the surface and sink back down via convection. This is just like water boiling on your stovetop. This makes the bulk surface of the star at times to appear to move towards us and away from us as those cells rise up and down. At a few meters per second, on timescales from minutes to hours, we call this granulation, and it can completely bury the signal of a small planet. Basically, the speed at which the whole star is moving back and forth due to the planet is less than the bubbly speed of the actual surface. And because this happens over minutes to hours, one way that we can try to deal with this is to take multiple measurements throughout the night, separated by a few hours, and then we can, in a sense, try to average it out. But it won't, of course, be a perfect cancellation. So here's a zoom out to give a sense of the scale of these bubbling cells. This is from the Daniel K. Inouye telescope in Hawaii. And the cells themselves, you can see, cover the whole surface of the sun, and they aren't that big on their own, only the size of Texas. Stars also pulsate radially, You can basically think of this as the star breathing in and out due to pressure waves inside them. And I'm not going to get into the physics of this here. If you're interested, feel free to ask us in the Q&A, or better yet, check out one of the past lectures by Jim Fuller on our YouTube page called Sounds of Stars. Anyway, the effect of this is that the star is pulsating outward, it is growing in size, and the face of the star that we see has a net motion towards us, which causes it to look blue shifted. And when the star is contracting, the face of the star is receding from us and it looks red shifted. These oscillations can be at speeds of a few to tens of centimeters per second, up to meters per second in speed, and are happening on timescales of a few to tens of minutes. For the sun is pulsating just like this every 5 minutes. So again, this is much greater than the signal due to an Earth-like planet, but we can try to average it out by either taking longer exposures, maybe 10 or 15 minutes or more, or even multiple quick exposures in a row and averaging them together. But again, this isn't perfect. Stars also have spots, and this is one of the hardest sources of contamination to deal with. The problem comes from the fact that the star itself is rotating. So you can see in this diagram here, the star is rotating from left to right. And if there are spots on the surface, a star spot is just a region of reduced brightness, these darker regions. And so if a spot is on the side rotating away from us, it will mean there is less red shifted light overall. And therefore, when we average the light across the whole star, we'll measure a net blue shift. And the same goes for the other side. The spots down in this bottom left might be blocking some of the blue shifted light, which will contribute to an anomalous net redshift. And as the star rotates, these spots move across different sides of the sun, blocking different amounts of redshifted or blue shifted light, and can mimic a planetary signal as much as 10 meters per second on the time scale of about the star's rotation period. But a complication with that is that these spots can appear and disappear and come and go on variable timescales. The spot that you see now might be gone by the time the star rotates around again, or otherwise might be a different size or shape and therefore blocking a different amount of light. And so while these might show variability on the timescale of the star's rotation period, which we can measure in many cases by the brightness variation, it won't be exact and it will be changing with each rotation. And to further complicate that, we know the sun goes through a magnetic activity cycle that lasts 11 years, over which we see different amounts of sunspots overall on the surface of the sun. So this bottom diagram shows the percentage of the area of the sun covered in sunspots. And you can see, even going back into the 1800s, we had data on this. You can see where there are more sunspots and fewer to more and fewer over 11-year cycles. And in some of these cycles, there are far more sunspots than some other cycles at their peak. Additionally, these sunspots actually move across the face of the sun. This top plot is showing the latitude where these spots exist. And you can see from, as you go through time, you sort of have these spots starting at plus or minus 30 degrees latitude and gradually moving towards the solar equator. And so what this means is that effect where sunspots mimic the Doppler signal from a planet will change in strength on 11-year timescales, which could mimic a long period planet like Jupiter, for example, at decades, orbital periods, and at tens of meters per second Doppler shift. And finally, short bursts of material off the surface of the star can also give a false Doppler shift of a few meters per second. These could be flares or coronal mass ejections, which is basically when the star burps some hot plasma out towards us. An example seen on the sun here, on the bottom left, there's this flare flinging outwards. Luckily though, these aren't periodic, so we can usually distinguish a planetary signal from flares, since a planet's orbit should repeat many times at regular intervals, but these will still, of course, contaminate the overall signal that we measure. And just a side note, if we want to look for a habitable Earth-like planet, where we say that when we mean habitable, we have just the right temperature for water to be liquid on the surface. So not too close to the star that it's too hot and that water evaporates to steam, but not too far away that the water would freeze, somewhere in the middle where it's nice and sunny and 75 degrees every day. So if we want to do that, we'd want to look around the smallest stars. That way, the Doppler shift induced by the planet is the greatest and the most easy to see, right? A smaller planet can tug on a smaller star more strongly than it can on a larger star. And further, the smaller a star is, the cooler it is, which means a planet can be much closer to its star and still be in that Goldilocks or habitable zone. And these smallest, coolest stars are called red dwarfs or M dwarfs and are actually the most common star in the universe. The problem is these red dwarf stars are the most active. They have the most frequent and strongest flares and coronal mass ejections. And with that in mind, not only does it make it more difficult to deal with the problem of stellar activity, but what does habitable mean in the context of such a star? If you're living on a planet orbiting an M dwarf, you better hope your planet has a good magnetic field to shield you at minimum. So this problem, which is called stellar activity, how all these different effects that we were talking about that are true to the star itself are plaguing our measurement of the star speed. And this may be the fundamental limit to the Doppler method for measuring exoplanets. As of now, there's a few ways to try to mitigate this. One is to just ignore it, in which case these effects contaminate your data and you might mistake discovering a planet when in fact it's really just the star being bubbly. We could avoid it where we choose stars to observe where we know or otherwise expect these effects to be minimal. Or better yet, we could minimize it by adopting smart observing strategies like averaging over the oscillations or the granulations. But all of these can still leave contamination that could bury the signal of a small Earth-like planet that's just 0.2 miles an hour. So if we really want to deal with this, we need to understand it. We need to develop accurate physical models of how this works and subtract this effect from the data. An entire other talk, in fact, an entire conference could be dedicated to the many efforts underway to solve this problem. Because if we can't figure it out, then it won't matter how precise of an instrument we build, as these small planets will go undetected, buried under the noise of the stars which they orbit. This is being called the challenge of the decade. So, like Cameron said, we normally have a stargazing component after the lecture. We obviously can't do that now because we're all at home. But I thought I would shout out this YouTube channel that was instrumental in my development early on getting interested in astronomy. This is the Virtual Star Party by Fraser Cain on the Universe Today YouTube channel. They get together a bunch of amateur astronomers and live stream their telescope setups and their live views of the night sky to the audience on YouTube and talk about all the different astrophysics going on in those systems. This is one of the main things in high school that really got me interested and hooked in astronomy. And I'm really excited to see that they just restarted these a couple of weeks ago after a several-year break. And so the next one is this Sunday. So check them out and enjoy the night sky from the comfort of your home. And with that, I'd be happy to take questions. Thanks.
Great. Thank you very much, Ryan. That was excellent. Could you turn off screen sharing? And can I invite the rest of our Q&A panel back, turning their video feeds on? Excellent. All right, so as I alluded to during the announcements, we'll go straight into our Q&A panel consisting of 6 different members of the department who work on a variety of different research topics, some related to exoplanets, some not. And we encourage you, I saw already that a number of people have been asking questions throughout Ryan's talk, which is great. Please feel free to continue asking questions in the YouTube comments section, and we will try and address those over the next 80 minutes or so. As we get started, what I'd like to do is go through and have each member of our panel introduce themselves briefly and talk about the kind of science that they work on that might give you guys a clue as to what questions might be more readily addressed by that particular participant. But for reference, like all of us have a pretty big, broad background, so we can try and address, even if we don't say that we work on the topic that you have a question about, we can try and take a stab at it. So I think everyone's familiar with what Ryan works on based on his talk. That was excellent. Thank you for the great review on all of that. I learned some things as well. I'm Dr. Cameron Hummels. I am a postdoctoral researcher in the theoretical astrophysics department. I do primarily work on computational modeling of how galaxies form and how they change over the billions of years since the Big Bang occurred, and try and compare the results of these computer simulations against observations of actual galaxies at different stages of their lifetimes taken with telescopes like the Hubble Space Telescope or the Keck telescopes or that sort of thing. I'm just going to go down the order on my screen. Samantha Wu, could you give us a description of who you are and what you work on?
Hi, so I'm a first year graduate student in the astronomy department here at Caltech, and I've done research on theoretical astrophysics related to bright and brief events like supernovae, stars being disrupted by black holes, or two stars merging together.
Excellent. Thank you, Samantha. Gao, would you like to speak for a moment? It should be noted that Gao just defended last week and is now Dr. Gao. He just earned his there was commencement today, virtual commencement. So he just got his PhD basically today. So congratulations, Gao. That's awesome.
Thank you, Cameron. So yes, my name is Gao Pinyanon, and similar to Samantha, I'm also working on massive stars that explode as a explosion called collapse supernovae. And specifically, I like to look at them in the infrared to try to see molecules and dust that are forming in those explosions.
Great. Thank you, Gao. Dr. Gao. Amruta, would you like to speak next?
Yeah. Hi, my name is Amruta, and I'm a postdoctoral researcher at Caltech. And I study stars that are left over after, a giant star goes supernova. And the stars I study are called neutron stars. So basically, I try to find them when they're young and when they get old over a period of millions of years, and what happens when two of them fall into each other and we see gravitational waves from them.
Terrific. Thank you, Amruta. And Agnes?
Hi, I'm Agnès Faté. I'm French, as you might hear. I'm a postdoctoral researcher at JPL, where I arrived almost 2 years ago. I try to understand why the universe's expansion is going faster and faster, so why the universe is accelerating. And I do that within the Dark Energy Survey collaboration, which image the sky on a large part of the sky. And my approach is to try to see if Einstein was wrong or not.
Excellent, excellent. Thank you, Agnes. Okay, so there have been a number of questions asked. Please continue to ask questions in our YouTube live comments. I'm just going to start off with referring several of the questions related to the topic that was just discussed in Ryan's talk, since that's most on people's minds right now. So Ryan, first off, there was one that was asked prior to your talk by 8-year-old Penelope. How do we measure the star's wobble? You addressed this for the most part, but I figure you could just give a real quick summary.
Yeah, for sure. That's a great question. And that's the question that everyone in the same field as me ask themselves how to do better and better. So the idea is the star is causing the planet to orbit because the star exerts a gravitational tug on the planet. And the planet is swinging around in that orbit, but the planet also has some mass and pulls on the star in an opposite way. It's much weaker, of course, because the planet has much less mass. It's very wimpy when compared to the star. And so the orbit that the planet makes the star move on is very, very small. It usually is much smaller than the actual size of the star itself. So it's only kind of doing this very slight wobble or tiny orbit in its location in space. And to measure that, we use this Doppler effect. So in those times in the orbit, when the star is moving towards our line of sight, we see that light get blue shifted. We see all those lines move more blue. And when the star is in that point of its orbit where it's moving away from us, it looks more red. And so if we can see that red and blue shift over time, then we expect that that's due to a planet that's tugging on the star and causing it to move in the same, with the same orbital period as sort of the time between red and blue shifts.
Very, very good. Very good explanation. A few other questions related to the context of the talk. Why are Jupiter-like planets also classified as young and old Jupiters?
Yeah, so I think these terms are used more in the context of direct imaging. So astronomers who are actually trying to take a picture of a planet. So planets are very close to their stars, and stars are way brighter than the planets. So this is really hard. You need fancy technology called coronagraphs, which have nothing to do with coronavirus. And you basically hold your thumb up and you block out the light from the star. And that allows you to see a very faint planet nearby. And it's easier to do this for younger planets and for larger planets. And why is that? If the planet is larger, it will have more energy and more heat from its formation, and it will glow more brightly. And if it's younger, it will still have all of that heat. It won't have radiated away into space. And so for these planets, which we can most easily directly image, these tend to be younger and more Jupiter-like planets, or even brown dwarfs, these objects 10, 20 plus Jupiter masses. And then old Jupiters would be something like the one that we have, which is 4.5 billion years old and relatively cold.
Right, okay, thank you. Another question that was related to some of the information you were providing. Two questions super related to each other. What about iodine is ideal for use during spectral analysis, and why is only iodine the only choice for the Doppler shift detection?
Yeah, so the one thing that makes iodine really nice for this is it has thousands and thousands of these absorption lines. And so you have many different sort of tick marks on your ruler that you can compare the star's spectrum to move back and forth with respect to. And we need all of these lines because, right, each line is only moving, 1,000th fraction of a pixel in size. So you need to average the bulk motion of these hundreds or thousands of lines to actually be able to pick up that motion and detect it.
Nice. Okay. How badly does the atmosphere interfere with the spectroscopy? Does our atmosphere, presumably?
Yeah. So for the Doppler effect, where it doesn't actually, it's not one of the most dominant sources of error compared to these other things that we were discussing. It does add those extra contamination lines, which can, in some cases, overlap with a line from a star, and then you can't use that anymore. Or it covers up some of the iodine lines and you can't use that anymore. But for the most part, it's actually okay. And actually, even if there's a little bit of clouds, we observe through clouds. It won't stop us as long as we can see the star and get enough light in a reasonable amount of time. What the atmosphere can make a big difficulty for is if you want to actually measure the spectrum of the exoplanet's atmosphere. And there's ways to do this where if the planet's moving in front of its star in the middle of its transit, you'll have some light that's going through the atmosphere on the sides of the planet that comes to you, and that will imprint the spectrum of the atmosphere on the star's light as well. And you can do this at different times when the planet is in front and when the planet isn't, and you can subtract the two to get rid of the star spectrum. And what you're left is what the planet's atmosphere spectrum is. And if you're looking for an exoplanet that's similar to the Earth, then you're also looking through an Earth-like atmosphere at this exoplanet somewhere else in the galaxy. And now you have the problem of what belongs to the Earth, what belongs to this planet. And that is a real problem if you're looking for Earth-like planets. So for that, you would really want to go to space and get rid of the atmosphere.
Makes sense. All right, the last one, I don't mean to make Ryan hog the show here, but there's a lot of really good questions related to his talk. One last one for now, before we move on to other members of the panel. Of all known and observable exosolar planet systems, do we have approximation as to how many are not viewed edge-on from our perspective, which could thereby negate some of the exoplanet finding techniques like transit?
Yeah, exactly. So we definitely want to consider this when thinking of just the total number of planets that might be out there, because not every planet is detectable. And even if it's big enough to be detectable, right, just like you said, it might be tilted in its orbit so that it doesn't actually pass in front of its star and we don't actually see a transit. And you can, the probability at which that happens depends on how big the planet is and how far away from the planet it is. So if it's really big and really close, you can make a lot of different angles where you still would see the planet move in front. But if it's really small and really far away, it's only a very narrow range of orientations where you can actually still see a transit. So this effect is different depending on the size and the distance away from the star of the planet, but it's about 1% of stars are in this nice orientation where you can observe a transit. So that's why for the Kepler Space Telescope, it had to stare at one patch of sky with, I think, a few 100,000 stars. And right, only a few thousand of those it was able to find planets in, because just 1% of them were oriented the right way in space for that to be detected.
Great. All right, so a few other questions for other members of the panel. One is, oh, this is good. What's the latest estimate of when the James Webb Space Telescope will become operational, or for that matter, become launched into space? Amruta, would you be willing to talk about this?
Yeah, sure. So James Webb Space Telescope is a very inspiring, large-scale infrared telescope that was supposed to be launched March 2021. But right now, because of the coronavirus delays that are happening, they're estimating that at some point during 2021, towards the later part of the year, it should be launched. We've all been waiting eagerly for this telescope to get launched, and let's hope that happens that year. So.
Indeed. Indeed. Yeah, it keeps getting pushed back, unfortunately, but hopefully it'll get up there soon. I read something that estimated that they were trying by the end of next year. That's the fingers crossed now. So. How about this one? What happens to stars after they merge? Samantha?
Yeah, so it can depend on the type of star, but for two stars such as our sun and a little bit bigger maybe, one thing that can happen is the two stars could just merge into a new star, but the new star would look pretty different from a typical star that, like our sun. It would probably be brighter, maybe rotating really quickly, so we'd see some interesting Doppler shift from that, like Ryan was talking about in his talk just now, and it might have a really high temperature compared to what a normal star would of that mass would have, so it would appear very blue. If the stars were like later in their life, like closer to being or have already become neutron stars or black holes or something like that, then it could become another neutron star or black hole. It's actually still a matter of research, but that kind of event would be one of the things that LIGO, the gravitational wave detector, could detect as well.
Great. Thank you. Thank you, Samantha. How about, well, I like this question. How cold is the universe? This seems like an appropriate question for Agnes.
Yes, so that's a bit of a change of topic, but I guess first we can start by reminding what, like how cold can stuff gets at all in the universe. So like the coldest stuff can get is actually minus 273 degrees Celsius. Because I'm European, I talk in Celsius, but I looked, wait, I need to look up what it means in Fahrenheit for you. I think it's minus 450 in Fahrenheit, something like that. So yeah, basically like matter can't be colder than that. The thing is, actually, the universe is, if you go like away from stars that are obviously like very hot, I guess Ryan can talk more about that. But if you go like in the void, space voids, it won't be actually the coldest temperature possible, because the whole universe is bathed in, is like filled with photons that comes from the Big Bang, basically, which is called the cosmic microwave background. And we measure this temperature, the temperature of this light to be 2.7 degree above the absolute zero, above 0 Kelvin. Kelvin is the units of the temperature for which zero Kelvin is the coldest temperature you can get. So yeah, basically the universe is as cold as 2.7 Kelvin, which is very, very, very cold. The fun fact is that we can actually construct instruments, build instruments that are colder than, even colder than that, which are just milli-Kelvin above the absolute zero.
Thank you. Thank you, Agnes. It looks like there was another question that might be appropriate for you in your research area. Can you talk a little bit about the recent measurements that suggest that revisions to the standard model of the universe might be in order?
Yes, that's a great question. I don't know exactly to which measurements this refers to, because basically all of cosmology today is about like putting more, like trying to challenge the standard model of cosmology, because there is a lot of unknown. So basically 75% of the universe, sorry, 95% of the universe is made of stuff that is, we don't really understand what it is. So 70% of that is made of dark energy, which is what, in a way, what repulse galaxies between each other, which dark energy is what like make the expansion of the universe going faster and faster. And there is also dark matter, which is a kind of matter that we don't really know what it is, but we know it's there because we see its gravitational effects, but it doesn't emit any light. So we can't see it directly. We have to find indirect ways to understand what it is. So those are two big things that we're trying to understand. And like, if we might just have to rethink the whole model when we understand in more detail what it is. Maybe it's a new kind of particle. Maybe the laws of gravitation are actually not what we expect, which is the area of my research. So that's what I meant by trying to prove Einstein wrong, is trying to prove that general relativity that describes the laws of gravity in the universe is actually doesn't hold on cosmological scales. But maybe what you're referring to is also another problem, is that we measure that, so the universe is expanding, and the speed of this expansion is, we are, not everybody totally agree on the value of the speed of this expansion. So some measurements show that it's 68 kilometers per second per megaparsec. And and others measure that it's like 72 or even 74 kilometers per second per megaparsec, which doesn't sound like a big difference, but actually at the level of our measurement, it is kind of a big difference. And we are working on trying to make measurements, make more precise measurements, different comparison between different type of observable, different type of measurement in the universe. So yes, we're working on it hard, but yeah.
Yeah, it is definitely really challenging. Okay, what's another good question here? How about a few more questions for our speaker, Ryan, on the topic of his talk? How do you tease out the signals of multiple planets orbiting a single star?
Yeah, so actually I'm gonna take over the screen share if I can do that.
Yeah.
So this is another YouTube video being screen shared onto YouTube Live. So it's like YouTubeception. But we have the TRAPPIST-1 planetary system here, which was received a lot of media attention because it has seven orbiting planets that are all pretty close to the Earth in mass. And a couple of them are at the right distance from their star to be in the Goldilocks zone. It's an M dwarf, so it is a very active star. So we have those considerations of what does habitable really mean. But you can see, this is the actual data of the planets orbiting. And you can see it sometimes they transit and it looks absolutely chaotic. There's each planet is labeled B, C, D, E, and F. And each of these dips corresponds to when the planet transits and there's less light. Here, there was actually a flare where it got really bright really quick. But you can see B has a constant depth, a constant amount of dimming, whereas the other planets are slightly different sizes or very significantly different in size. And so the amount that the light dips is different for each one. And so you can track based on how far down the dip goes, which planet is which. And you should also be able to confirm that by making sure the distance between equally deep transits is the same for the same planet. So the orbital period for B should match from each one to the next. And there are many cases during this where you could see multiple planets transit at the same time, kind of like that animation that I showed, in which case you can get some weird shapes, which you need to be a little bit more careful about how you're modeling that data. But using the different properties of each planet to sort of distinguish which signals correspond to which planet and determining from that how many planets are in the system. And it's a similar thing with the Doppler method too. You have different periods associated with the redshift and blue shift, and you have different strengths. And so when there's a lot of planets, it can become pretty complicated and you need a lot of data to be confident in it. But because of those different timescales and those different sizes and strength of the signals, you should be able to distinguish it.
Thank you. Thank you, Ryan. There was a question here. Are there signs of new chemistry from the absorption spectrum of exoplanets? Something like chemistry that's not happening here or that we knew about prior to that here in our solar system?
This for me?
I think so. You're the exoplanet master here. Perhaps
yeah.
So I don't things to chime
I will speculate, but I don't study atmospheres of other planets. But something I would think about is if you're measuring the different kinds of chemicals or molecules or whatever is in the atmosphere of this other planet, then if you're looking for signs of new chemistry specifically, I would want to make sure that everything that we have experienced on Earth and everything that we know about with chemistry is insufficient to explain what you see in the data from another planet's atmosphere. And when you've sort of worked through all of those possibilities and it really truly is nothing like we've ever seen before, then we have to start getting creative and thinking about new ways in which stuff might interact. But to date, I don't know of any cases of that. Usually we see things like water vapor in some planets, which gets a lot of excitement, or like CO2 or methane. The usual suspects we see.
Right. How about, this question seems related to what Samantha was discussing before. Is there any reason for star mergers to occur, or is this just a regular space event?
Yeah, so I guess kind of the answer is yes to both. It is fairly common for stellar mergers to occur because about a third of all stars are in binaries. So you need a binary to have a merger in the first place. And if the binaries are made up of massive stars, then about a quarter of those stars are expected to merge within their lifetime. So in that sense, it's kind of common. But how it actually happens, which maybe that question is also getting at, is usually what happens is when the stars go off the main sequence, as in the sun is on the main sequence right now, but eventually it'll leave this stage and expand into a red giant. So all stars do this. And when that happens, the expansion can sometimes lead to the envelope of that star engulfing the other star, or maybe just transferring some mass over to it. And that phenomenon can lead to the stars merging. So that's one scenario, although there can be others scenarios. But
what happens to stars when they die? Guess there's a few people who can respond to this.
Yeah, I think almost all of us can respond to this. I would take one for the team. So yeah, so stars, like the ones that you see and ones that are bright in the sky right now, they have a nuclear fuel, that they have been using, and this fusion reaction is driving the electromagnetic emission, the light that comes from the stars. And most of it is hydrogen. Towards the end of the life cycle of star, the hydrogen starts depleting to a point that there's no more hydrogen left. Now, some of the stars, the more massive stars, keep on, with the fusion processes by fusing more and more heavier elements. And so, if you start out with a star that is less than 1.4 times the mass of the sun, our sun, it would end up in what Cameron had earlier referred to as a planetary nebula, wherein the star, when it dies, its outer shell is still, hanging around it like a ring, and the inner core is still able to radiate this ring. And this ring can actually also have different shape. It doesn't necessarily have to be a ring. There are so many beautiful patterns if you Google just the word planetary nebula. Now, if you're looking at more massive stars that are more than 1.4 times the mass of the sun, they puff up into a supergiant phase. And then after this phase, what happens is they undergo a supernova explosion. In this process, the outer shell of the star gets blown away. And then what you're left with is the core of the star. This core of the star is actually super dense because it consists of all those heavy elements that the star was focusing on fusing towards the end of its life cycle. And this core weighs, if you just take, like a pin of this, like just a little bit of this, a pinch of this star, it would weigh as much as the Manhattan. So in a 10-kilometer radius, you're basically compressing the whole of the sun. So these are the stars that are formed when you have giant stars that undergo supernova explosion. Sometimes these stars are extremely giant and their core that's left behind starts collapsing onto each other, forming a black hole. So stars end up in different sorts of spectacular ways depending on how they started.
That was a great response. Thank you, Amrita. Let's see, lots of Lots of questions. Can you use the Doppler effect to measure a planet around two separate stars? Don't the stars cause each other to wobble?
Yeah, exactly. And the stars are much more massive than the planet, so you'll get this huge swinging of redshift and blue shift from the stars on each other. But then within that, you might be able to see a much smaller variation due to a planet. There are lots of examples of these, mostly discovered with, or some discovered with transits, where you can see the planet maybe transit one to the star or the other. But also there's a bunch of radial velocity Doppler method examples of these. If you just, I'm blanking on a lot of the names, but if you just Google circumbinary planet, that's a case where you have two stars in orbit about each other, and then you have a planet that circles both of them. That's one possible configuration. Like that's what something like Tatooine would sort of be like, where there's two stars in the middle and the planet orbits both. You might also have two stars orbiting each other, but only one of the stars actually hosts a planet. And in that case, there'll be times when the planet is sort of in between the two stars or only on the side of one. So you'd have some pretty wild seasons there for sure. But yeah, you can definitely find planets like this around binary stars, and half of the stars in the sky are in binary or more higher multiplicity star systems. And so there's a lot of interest as to how this affects planets in the context of habitability and just in the context of what kind of planets can survive being around two stars as compared to one, because there's a lot more gravitational chaos.
Thank you, Ryan. Here's a slightly different topic. Would you recommend any introductory papers or books for a 9th grader to gain exposure to astrophysical concepts? This is potentially something that all of us can respond to in some capacity. The two that jump to mind for me are Stephen Hawking, A Brief History of Time. And there's a book, I don't know if you guys have encountered this. It's called Mr. Tompkins in Wonderland. It was written, I think, by George Gamow, a famous physicist. And it's fiction, but it puts it in the context. Follows this character named Mr. Tompkins around, but it puts it in the context of how he encounters certain physical realities, like the effects of relativity when the speed of light is shrunk down to a much lower level, on par with how quickly a car can drive, something like that. And what kind of counterintuitive behavior you experience when these, which is relevant for the universe, but it's put when the constants are slightly changed to more relevant to our life scale. So it's pretty interesting. Do other people have other suggestions of books or papers?
I don't know if you could see it.
Sorry.
Obligatory Cosmos by Carl Sagan.
Yeah, that's good.
Absolute must.
And I guess I was going to say, my first introductory astronomy class I ever took, we read this book called A Short History of Nearly Everything by Bill Bryson, which it has some biology related things too, but it also explains a lot of really cool astronomy stuff, and it's basically what got me into this. So I highly recommend it.
Any other topics?
I would say if you're a young girl in 9th grade looking for a book, I would say read Hidden Figures. That's a really excellent book. It's about astronomers that were, sorry, not astronomers, but like the rocket designers who were not really given their fair share. The other book I would say is Glass Universe by Dawa Sobel, and it's about some of the first astronomers, women astronomers, who started astronomy by looking at glass plates to try and they with their hands and just with their eyes they catalog millions and millions of objects, which then male scientists published in their papers without any accreditation to these scientists. So I would highly suggest reading about their stories. It's really interesting.
Great. Any other additions, or, I mean, that's a pretty good list. It's a lot of reading to give to someone. Okay. Jumping back into the science, the expansion of the universe has been shown to be accelerating. Did we have the same acceleration throughout the entire age of the universe? Seems like a good cosmology question for Agnes.
Yeah, great question. So maybe we can start to summarize the history of the universe. So since the Big Bang, the universe has been expanding, but just after the Big Bang, this expansion has been actually accelerating. It was like insane expansion in like a very, very short time. That's what we call cosmic inflation. At least we think it happened, but we are still trying to show definite proof that this period has happened. So that's one first period where the expansion went like mega crazy, and then it's kind of like slowed down. So it stopped accelerating, but it kept expanding. And then, so that was 14 billion, around a bit less than 14 billion years ago. And then around 6 billion years ago, it starts accelerating again. So another way to see that is that we think that dark energy is at the origin of this acceleration. And basically before it was too diluted, so it was not like strong enough to cause the acceleration. And so then, the contrary, like there was much more matter than dark energy. So gravity was taking over the acceleration. So the expansion was decelerating. And then 6 billion years ago, dark energy took over and this acceleration of the expansion started again. So the question of, is this acceleration constant or not? I think we're still trying to figure this out because this depends on the properties of dark energy, exactly. But that's one thing we're working on now with like big galaxy survey, so like big telescope that image galaxies in the universe. But one of the theory is that if the universe expansion is acceleration is going like greater and greater with time, at some point we will have what we call the big rip, where basically there will be a huge rip of the universe, and I guess, yeah, the universe won't exist anymore because just space-time will be ripped, which is not very nice, but we're working on that to know if that will happen or not. But that will be like in billions of years if it happens, so don't worry too much.
Yeah, I try not to worry about this. A question for Gao, our newest doctor. Do bright and brief events affect exoplanet observation?
Yeah, so I think Samantha mentioned that in her bio, that for these bright and brief events like supernovae can, of course, if you have an explosion at the center of the solar system, that's a very bad day and bad news for all the exoplanets orbiting around that system because they're unlikely to survive. However, one thing we know, which is quite surprising, is that actually first exoplanet systems that we know was discovered before 51 Pegasi b in 1995. And there were a system of smaller planets orbiting neutron stars. And we know this because that neutron star happened to be something we call a pulsar, which means that this neutron star sends out beams of radio waves. And when the neutron star rotates around, this beam of radio wave come into our line of sight and then turns away and then comes back and turns away. So what we observe is pulses, very, very regular periodic pulses of radio waves coming at us. And because these are so precise, this is actually like one part in astronomy that we can make measurements like down to, with many significant figures, and we can measure this period very precisely. And because of this precision, some radio astronomers were able to actually measure that the change in period in this neutron star infers that there are some planets orbiting around this neutron star, tugging it a little bit. But unlike Ryan's stars, these measurements are intrinsically just much more precise. So you can find exoplanets down to like lower than 1 Earth mass. However, these systems turn out to be extremely rare. And my understanding is that currently we think that these must form from the fallout of the explosion of the stars. And we don't exactly know how this happened quite yet. And again, because these systems are so rare, we simply don't have enough examples of them.
Thank you, Gao. It looked like there was another question here. How can we use the James Webb Space Telescope to study topics that members of the panel study, like exoplanet, supernova, cosmology, stellar mergers? Yeah, so JWST, as we've already discussed, has been in planning for a long time and manufacturing for a long time, but since it's kind of the successor big space telescope mission to succeed the Hubble Space Telescope, it's going to be able to address a lot of different areas of science. Gao, perhaps you want to address how it'll impact the field of exploding stars and supernovae?
Yes, so I'm super excited about James Webb. I've been waiting for so many years now, but I'm very ready to use it. And the reason is because I study these supernova explosions using infrared light, which is actually what James Webb is going to be doing mainly. And infrared observations from the ground is the royal pain in many ways. So during the talk, Ryan mentioned a couple effects that the atmosphere can have on spectroscopy, and that in the optical is not so much of a problem. It presents some challenges, but it's not a game changer or a deal breaker for our observations. In the infrared is totally different. So for some context, in terms of wavelength, the optical light that our eyes can see is from about 400 to 600 something nanometers. Once you get out to 1000 nanometers or 1 micron, beyond that, sensors like those we have in our cell phones and our typical camera cannot detect light anymore. So in the modern definition, we typically take 1 micron and longer as a cutoff for infrared light. And from the ground, we can do pretty well up until about 2 microns, from 1 to 2 microns. The sky is getting brighter and brighter with wavelength. And this is due to the emissions, both from water molecules in our atmosphere and also just thermal emission from the sky and also our telescope. So one thing that so the first thing we have to fight is that this background radiation that has nothing to do with our star is getting brighter and brighter with wavelength. The second thing we have to deal with is that these water molecules that produce fantastic spectral features for us to observe in exoplanets are also present in our own atmosphere and also eat all the infrared light. So I don't have anything to show. I don't have a plot to show, but it turns out that water, methane, and carbon dioxide in our atmosphere are extremely good at trapping infrared light. And this is also the same reason why there is such a great so-called greenhouse gases, because just a small amount of these gases in the atmosphere can trap infrared light and turn it into heat. And this is also why emission of these gases are such a huge problem. For infrared astronomy, this means that as you get longer into wavelength, you cannot see any light coming through the atmosphere anymore, because all these molecules in our atmosphere just eat them all up. So of course, James Webb will fix all this, because it will be launched very far away from the Earth. So it will be well protected from all these atmosphere effects. And to round this off, why do you want to observe supernova in the infrared? And the biggest reason is that after this explosion happens, actually a lot of chemistry happened in the fallout of the explosion. I talked briefly about this exoplanet formation. We don't know much about those yet, but we also know that a bunch of molecules can also form, and dust grains can also form in the fallout of the supernova explosion. And from the ground, we simply cannot make these observations. So we have to wait for James Webb for us to be able to do this. And just one last thing before I stop talking. Just for a quick comparison, I and some of my collaborators, as part of my thesis, did this kind of novel observation at 10 microns. So this is 10 times the wavelength of the start of the infrared cutoff of this one very bright nearby supernova from the ground, using one of the best telescopes at one of the best sites that we have. And we took 6 hours of the telescope time, a huge 8-meter telescope. And we detect a very, very faint point in our image, just barely enough for us to claim a detection. That same observation, if you do with James Webb, can be done in about 1 minute of the exposure time on James Webb Space Telescope. And it will produce the data 100 times better than what we got from the ground. So this is the reason why I'm very excited about Webb.
That is exciting. I can speak a little bit about how it'll influence the field of galaxy evolution, the observations of James Webb. So as Gao alluded, James Webb is primarily operating in the near infrared part of the spectrum. Near to mid infrared part of the spectrum instead of the optical, like Hubble is operating. And so because many of the objects in the universe, as Ryan discussed with the Doppler shift, and are redshifted away from us, primarily distant galaxies and such, due to the expansion of the universe, the farther away they are, the more quickly they're traveling away from us. And so the more redshifted they are. And so it takes the light that they would normally be emitting in the visible wavelength, what we'd see nearby, you take those same galaxies, you place them on the other side of the universe, they're moving farther away from us and faster, and that light gets shifted into the infrared. And so so in terms of galaxy evolution, James Webb is really going to open up a new window on the sky of the most distant galaxies. And because the speed of light only travels at a finite speed, that means the most distant galaxies are we're seeing the light that came off of them when galaxies were much younger, when the universe was much younger. So we're effectively able to study galaxies when they were kids, when they were infants, just after the Big Bang. And while we've had some observations of that using Hubble or using other instruments, it's really going to open this up much more dramatically to see the universe when it was much, much younger. And because James Webb is a substantially larger aperture telescope than Hubble, it'll be able to collect more light and be able to do things much faster, to observe things much faster. So that's, I'd say, the primary way in which it's going to advance galaxy evolution. Do others have, sorry, I'm phasing out here. I feel like I'm Marty McFly in Back to the Future. Got to do something about this. Do other people have things they want to add about how James Webb may influence their respective fields? It's okay if you don't.
I can quickly add a tiny bit of a thing.
Great.
Yeah, so earlier we talked about the supernova explosion, and at the end of, like this explosion, you have this neutron star sitting inside, the bubble that's receding the outer shell. So this neutron star also has a very energetic wind of particles that comes out of its poles. And then this emission, these particles expand into the surroundings that are trapped by the outer external shell. This forms something called as the pulsar wind nebula. And it's really beautiful because, this pulsar wind nebula, if you look at the Crab Nebula, you see like really complex filaments kind of structure, and the neutral star is sitting inside of that. So now with IR, like infrared observations that are possible, with JWST, you would be able to look at, like the structure of the pulsar nebula itself, if there are, intense shocked emission as it ramps into the surrounding, this nebula, which is like a shell, as it expands into the surrounding, if there are shocks inside of it, how it is, not only that, but also how the pulsar is also injecting energy into this nebula. And I think that would be one of the first sites that we would have on understanding pulsar nebula in this way with JWST. So, yeah.
Cool, very cool. Okay, I'm going to move to a different question. There was a question about the open source software visualization tool that I showed at the very beginning called Stellarium. Can you talk about the Stellarium project, how it's relevant to researchers, astronomers, and how developers or citizen scientists can contribute? I don't know how it's being developed. I know it is developed open source, but I think there are some primary developers involved in its development and writing of the code. I know that there are a number of tools that different groups have created for doing visualizations of the sky or aggregating many different actual data sources into their software tools. So you're looking at real data of where the exoplanets that have been discovered up to date, like where on the sky they are, or data that's been taken from the Sloan Digital Sky Survey and where those galaxies and stars are. So you're actually, it's not just some make-believe universe in your computer that you're looking at. It actually represents what we've discovered in the sky and keeping up to date on things. There's a product that originally was hosted by Microsoft called the Worldwide Telescope, that was then donated to the American Astronomical Society, that does this sort of thing and aggregates different sources, but it's meant as a tool that educators and astronomers can use to quickly understand a bunch of different data sources, what the sky looks like in X-ray, what it looks like in the visible wavelengths of light, what it looks like in infrared, the radio, and so on and so forth. There's the virtual observatory, which I think seeks to do the same thing. In terms of high-level, nice visualization tools that you'll see being used in planetaria, there's one that's an open source project being developed primarily at the American Museum of Natural History that also has a number of really great talks online that you can find both on YouTube as well as Facebook Live. They have a tool that they're developing called Open Space, I believe is the name. And yeah, Open Space. And there's a number, I believe, since the shutdown has occurred and people have been stuck at home, one of the primary operators of that code at the Museum of Natural History in the Hayden Planetarium, his name is Carter Emmart. He's been doing a couple times a week, he'll go live and on Facebook Live or on YouTube Live, and you can connect and see him kind of zoom in on different places on the surface of the Earth as it's showing like real satellite data, and then zoom out and show different stellar systems and different galactic systems. It's really nice. It looks really good. I mean, the Stellarium code that I was operating from my laptop just a few minutes ago is great for what you can do at home, but that Open Space is like professional level. So I encourage you to check that out. I think the download, if you want to get it running, is quite substantial. But in terms of how we use it as scientists, I, for one, will use it primarily in planning basic observations that we do during our public education events, like what's going to be in the sky at whatever point that I need to look. But I'm not an observer. I primarily work on computational modeling and theory. So observers have their own tools for calculating what's going to be up in the sky at what time from what vantage point, and from this observatory in Chile, or from this observatory in Hawaii, or in the Canary Islands, or wherever the Hubble Space Telescope is in the sky at that particular moment. So stellarium's a good guide, but it's not usually used at a professional level for planning professional observations. That's what it is. Does anyone else have anything to add on that topic?
I can add a little bit to that.
Yeah.
Oh, yeah. So I work mostly as an observer, and as Cameron said, we usually have like some other software that are more like automatic. You can put in like a huge list of your targets, and it will compute like where on the sky and what time they will be visible for you. The problem with that is that when you automate things a lot, you get like output in chart and graphs, and they're not as visual as you get on Stellarium. So I have a small embarrassing story, which is that I went through all this exercise, put in my target list, compute all the positions, show up at the telescope, punch in the coordinates, and sure enough, it was right next to the moon. And this is because some of these codes don't really tell you if the moon is next to your target. So if I have used Stellarium to kind of gauge the rough location of where my target would be, that would have been prevented.
So why is it, can you tell us why it's bad if your astronomical target is right next to the moon?
Yeah, so when you observe a star or whatever you like to observe, you're competing between, the competing source of light and noise is mostly your star versus the emission from the sky. So for me, I work in the infrared. So this is even a bigger problem because the emission from the sky is really bright. Now, in the optical, this is much worse because the sky is typically really dark. And if you put the moon close to it, suddenly the scattered light from the moon can overwhelm your target. In the infrared, we usually don't have that problem because the sky is already really bright. So we are already limited to relatively brighter sources compared to our colleagues in the optical. But when you get really close to the moon, that is still overwhelming your detector.
Thank you for that.
Yeah. Don't do that. Always have a backup target.
Here's a question, seems appropriate for Brian based on his talk. What have you detected or found or learned after more than 20 years of investigating the very first original exoplanet observed?
Yeah, so we've learned a lot. It's basically been a sort of revolution, to say, in science, of just how much more about what is out there. We've sort of figured out that, for one, planets exist outside the solar system, and just the incredible diversity of them. One striking feature in the population of exoplanets that we've seen is that the most common exoplanet is actually somewhere between Earth and Neptune in size. That's the most common planet in the galaxy, and we don't have anything like that in our solar system. The more we sort of seem to be observing, and granted, we're most likely to detect close-in and massive planets, but the solar system is it's still sort of this unique architecture of planets compared to what we are seeing with like the Kepler Space Telescope and with these Doppler surveys. There's actually one of the past Caltech Astro outreach talks by Dr. Arpita Roy called "We Were the Discoverers" is an excellent talk. She goes into way more depth and explains this much better than I could without any nice pictures or slides or anything. So go check that out if you're interested in sort of the history of exoplanets and like sort of highlights of what kind of planets are out there, like rocky and gaseous and Jupiter, or what we call mini Neptunes and all of that stuff.
Yeah, Arpita's talk was excellent. Here's a question that we got a while ago, but I can still try and address, is the cosmic web fractal, i.e. the same physics can occur at multiple scales? So this is a really interesting question. Many of you may be familiar with the idea of fractals. This is, as the question suggests, when you have self-similar behavior in a system. That is to say, if you zoom in a bunch, you'll see the same kinds of structures at smaller scales that you do at larger scales. And we do see this kind of behavior in the universe. For instance, jets. In certain stellar systems, like when a star is collapsing or there's something going on in the interior of a star, you might have jets that are like bipolar jets that are flying out from two regions in the star. And similarly, on galactic scales, which are billions of times larger, you see jets being propelled outward by very different interactions, but ultimately it's the same kind of physical mechanism or maybe different physical mechanism, but the same kind of effect on a much larger scale. But scientists have looked into this because it is interesting to think about how the universe might have this self-similar behavior on many different scales. And there's actually a bunch of theories of cosmology that the universe are called fractal cosmology theories that are backed by this. But the question specifically asked about the cosmic web. I'm going to show a couple of graphics here, if I can. Okay, so to start out with, first, can you guys see this okay? This is, you may have heard of this. There was a famous French mathematician named Francois Mandelbrot who first posited the idea of certain mathematical sets that show this fractal behavior. And what we're doing is zooming in on a visual representation of a Mandelbrot set that shows, as you can see, as we zoom in, we see similar structures like this weird oblong egg kind of structure at much smaller scales than the original structure. So we keep zooming in and we see this similar behavior. Does the universe or does the cosmic web behave this way? The cosmic web, this is a nice graphic representation of the cosmic web as was done with a computer simulation called the Millennium Simulation about 10, 12, 15 years ago. And what it represents is the distribution of matter on very, very large scales. Now, when I talk about very large scales, I mean on the order of the scales of the universe, like 1 billion or several billion light years across. It doesn't have a bar on it to show what a distance scale is, but you get the idea that it's very, very large scale. And this is what we believe is the structure of much of the mass content in our universe. And the dark areas represent voids. Our last public lecture was given by Mia de los Reyes. She talked a lot about the distribution of galaxies and voids and filaments in our universe. So this is relevant. And I think this is when this question was originally brought up. So the dark areas are voids or low density regions. And then the bright areas are filaments or walls or high density regions. And that tends to be the places where galaxies or clusters of galaxies tend to form. And you can, if I were able to, I mean, I guess I could try and, this is only such high resolution. I'm zooming in and you're seeing that I'm not zooming in like that other movie was, but you're able to see that there does appear to be some self-similar behavior. Now, that's true for the most part, but it turns out that it breaks down on very large scales. So you have stars, you have collections of stars are clusters, like that Hercules cluster we looked at before. Collections of more stars, you tend to find galaxies. Collections of galaxies, you find clusters of galaxies. Collections of clusters, you find superclusters. So matter tends to collect and coalesce into structures that are similar on many different scales, but that breaks down when you go to very, very large scales. And that's simply because the universe has only been around for a finite period of time. It's only been around for on the order of 14 billion years. And so it takes time for structures in the universe to coalesce and to form. And the larger the structure, the longer it takes for that stuff, the material, to get into that, because structures tend to form hierarchically in the universe. So you'll form small stuff, and then those will merge into larger things, and merge into larger things, and merge into larger things. And because we haven't had an infinitely long time since the Big Bang, there hasn't been enough time to form the larger and larger and larger. So our self-similarity breaks off at a certain level, above the scales of superclusters or so. And there we find, based on observations, that the universe tends to be more homogeneous. It tends to be more uniformly distributed once you get to a large enough scale, instead of this kind of clumpy behavior. So I hope that addresses the question for the most part. Let's see, what other questions do we have here? Is there any chance of teasing out a binary planet like our Earth-Moon system with the Doppler method of detecting exoplanets?
Yeah, that's a great question. There are people who are trying to do this. Look for these so-called exomoons. So we know there's lots of exoplanets. These are planets around other stars, but we haven't found yet a moon around one of those planets. We would expect them to exist. Like Jupiter has 70 plus moons, Saturn has 70 plus moons, the Earth has one, Mars has 2. Like there should be lots of these exomoons or even binary planets. There's been one candidate detected by the Kepler Space Telescope and the Hubble Space Telescope, where this wasn't the Doppler method, this was the transit method. So what these astronomers saw was basically a planet transiting the star and then a moon transiting it right behind it. And over time, you would see sort of the moon transiting along with the planet, and it would be at different, like on either side of the planet, depending on where the moon was in its orbit around the planet. And in this case, this is something like a Jupiter mass planet with a Neptune-sized moon. So more of like a binary planet. And I haven't been following it too much, but there's been a little bit of debate as to whether this is a real system or if it's like false positive detection. I would hope it's real because that'd be really cool. That'd be the first exomoon discovery. Something like the Earth and the Moon, which is on a much smaller scale, would be very difficult to detect. We can't quite see moon-sized objects in transits. It's too small, really. The amount of light that it blocks isn't enough to detect. But with the Doppler method, if we were to sort of think long-term in the future with very, very powerful direct imaging techniques, like really, really good coronagraphs, so you can block out the light from the star and just look at the planet, then you could measure the Doppler shift from the planet's speed as it goes around its star. And if you do that, maybe you might see the planet wobbling. And so you're taking this problem of seeing the star wobble to directly seeing the planet wobble, which could be because there's a moon tugging on it. That's not something we're capable of doing in the near future, but that's a really exciting future prospect.
Thank you. Slight change of topic. What would be the result if a merger occurs between a magnetar and a black hole? Would it produce a short gamma ray burst?
Okay, so that's a very interesting question. Okay, so magnetar is basically a neutron star on a steroids. It means it took the normal magnetic field, which is about 100 trillion times the fridge magnet, and then just multiplied it by another million or so. Let's imagine that. Okay. So now it depends on, imagine this is like a WrestleMania, and it depends what kind of a competitor the neutron star is really, the magnetar is really meeting in the ring, right? If it's going to meet with a really supermassive black hole, which can weigh, millions of times a normal of our sun and like more, of these sizes, then it's not a fight, because then what's going to happen is that this really supermassive black hole, even before this magnetar enters, something like the event horizon of this black hole, just tidally, what it would start doing is like start squishing and elongating the neutron star as it's coming closer and closer because of the intense gravitational field. And when this happens, slowly the neutron star, even though it has this crazy magnetic field and very strong gravity, it would start breaking apart. And so tidally, it's kind of like, it's coming loose, and it's called the tidal disruption event. But this is also a very spectacular event because, you kind of see a long scale, like, devouring of the neutron star by a black hole. Now, this is one scenario. The other scenario is if a magnetar meets a normal sized black hole. So a normal sized black hole here is, let's say, less than 100 times our sun, okay? So if this happens, we should in fact see some sort of a gamma ray burst that accompanies it, unless it's very far away or like, it's depending on like, what kind of an inclination angle this kind of an event is happening at. But if it happens with the right sort of parameters, because the magnetic field is so, because the magnetar and the black hole are merging into each other, we should see a short gamma ray burst. But so what is a short gamma ray burst? So that's the other question. So a short gamma ray burst is an intense flash of electromagnetic radiation that you detect with gamma ray telescopes. And sometimes it's a much shorter lived burst because it's less than about 20 seconds or so. And so in fact, last year, we did see a neutron star and a black hole merger, which was seen first of all by LIGO, which is the Laser Interferometric Gravitational Wave Observatory. And basically they detected when these two objects were falling into each other, there was an intense gravitational radiation, which are like the ripples on space-time fabric that it gave off. And immediately LIGO detected, oh, there is a disturbance in space-time. And at the same time, the Fermi telescope, which is a gamma ray, it has a gamma ray burst monitor, which is basically staring at as much of the space that you can with a big gamma ray instrument, and they detected this kind of an intense flash that came through. This was in the August of last year. And so, yeah, and what happens is once you have had this gamma ray burst, it would have much after, long after, you can still see it in other wavelengths that can help us confirm what kind of a star fell, like what kind of a neutron star was it, what was its mass, and all of these other parameters that can confirm if it was a magnetar or not. So that would be my answer. So thank you. That was a really exciting question.
It was. I like this one. How do dying low mass stars produce heavy elements? You have a couple of dying star people here.
I guess I can answer it. So if you're a low mass star and you die, then you should become a white dwarf. So like a star like our sun would become a white dwarf. And for white dwarfs to synthesize heavy elements, for white dwarfs to synthesize heavy elements, what can happen is the white dwarf can be ignited to explode by maybe some material falling onto it that starts a thermonuclear runaway on the surface of the white dwarf. And if that happens, then that can cause, basically it's like nuclear fusion is happening through this process, just like what happens in the cores of stars, like our sun. And this process can synthesize heavier elements than, hydrogen or helium. But also, if you are able to ignite a type 1a supernova, which is if the whole white dwarf explodes, then in the explosion, elements up to like nickel and cobalt can be synthesized in the explosion and then radioactively decay. So that's like so during the actual explosion of a type 1a supernova is another way a low mass star can make a bunch of heavy elements. Yeah.
Interesting. Okay.
If you tune into Mia's talk last time, you will also learn that most of the iron in the universe is produced by these type 1a explosions.
Excellent. If it were, yeah, this is kind of a good question to finish off on. If it were determined that an exoplanet could foster life, i.e., that star lies within the Goldilocks zone of the planet's host star, as we saw during Ryan's talk, how would the scientific community proceed with study regarding that particular exoplanet?
Yeah, that would be really, really cool. And someday this will happen. And a lot of people have thought about exactly what to do. So if JWST is in space, it will definitely point at it first, because we really want to know what the atmosphere of this planet is like. If we confirm that the easiest way to know if a planet is rocky is to measure its density. And if it's dense like rock, then we can expect it to be rocky as compared to gaseous like Neptune. And you can do that if you measure both the size and the mass. So this would have to be a transiting planet so that we can measure its mass from the amount of the star's light that it blocks, but then also measure it with the Doppler technique and measure its mass based on the wobble that it induces on the star gravitationally. And if we have this rocky Earth mass planet in the right spot around the sun or star that you would have the right temperature for liquid water, then we'd want to check, what is the atmosphere like? Is it similar in composition to the Earth's? Does it have mostly nitrogen? Does it have oxygen? Things that we would expect sort of to be products of life, what we call biosignatures. So things like methane in some cases, although that's not always necessarily from organic activity. There's also interesting ideas going towards technosignatures. So this isn't just looking for signatures from life, but signatures from civilizations, such as like the lights that cities might emit on the night side of a planet, potential like mega structures of satellites or the Dyson spheres or things like that, which would be pretty wild. But if we see something that looks like that, of course, we'd want to make sure it's not something more boring, but sort of more easily occurring in nature, like a dust cloud from a comet or something like that. Yeah, so I guess for me personally, I would want to sort of go down the list of what makes a planet habitable and does that exist on this planet? So things like water, things like an atmosphere, you know, does it have taco trucks, things like that make it worth living? That might take a little bit more observation, but are important questions for us to be asking ourselves, I think.
What size aperture of a telescope do we need to resolve taco trucks on the surface of an exoplanet? These are the questions driving astronomers. I don't know. A lot bigger than JWST.
Well, there's that idea to use the sun as a gravitational lens and park a spacecraft like 500 AU out in space.
That's a long way to go.
That's a lot of technology that needs to be developed to get there, but that might be able to do it.
Out in the Oort cloud, just having something hanging out there. Yeah, then we could detect the taco trucks. All right, I think we're probably at the end. I'm losing steam here. I want to thank all of our panelists for their attention and great responses. In particular, our speaker tonight, Ryan Rubenzahl. Thank you. That was great. For our audience, thank you for attending. As I said, we have these every month. I haven't set the date for next month's, but stay tuned on our social media and on YouTube and on our website. I'll announce it all of those places. And in the meantime, we'll have our Astronomy on Tap a week and a half from now, a week from Monday, the 22nd of June. It's on our YouTube channel. You can the event is already set up, so feel free to set a reminder and check it out. It's going to be fun. It'll be on gamma ray bursts and space rocks by planetary scientists. It should be really good. So thanks for coming, and I think that's it. Have a great weekend, everyone. Thanks.